Singh. Sankalp sir, are you there?
Yes, ma'am. Good evening.
Yes, very good evening. So yes, I welcome you on behalf of Department of Electronics and Communication, V.V.P. Engineering College. And you have been your profile has been made a presenter. So while I'll be introducing you to all the participants, I would just request you to once verify. Are you now able to share your PPT?
Uh, can you check if my screen is visible?
Oh yeah. Oh yes, it is. Yes,
Okay.
sir.
Okay.
Yeah. Okay. So very good evening to all the participants. I would like to introduce you to our today's speaker, Mr. Sankalp Singh. Dr. Sankalp Singh heads Synopsys Academics and Research Alliances program in India. The main role of him is to bridge the gap between the industry and academia and drive the workforce development initiative. Prior to joining Synopsys, he worked as an assistant professor at Geetham University, Bangalore, in the Department of Electrical and Electronics Engineering. He has done his postdoctoral fellowship on simulation and design of GAN HEMTS for high frequency applications using Synopsys TCAD from International College of Semiconductor Technology, that is ICST, at National Yang Ming Chiao Tung University, Taiwan. He did his PhD from NYCU, Taiwan, on simulation and design of tunneling field effect transistors for low power applications under the Department of Material Science and Engineering. He was a visiting research scholar at UC Berkeley under Professor Chen-Meng Hu in 2016. As part of new southbound policy of Ministry of Education, Taiwan, Dr. Sankalp has coordinated multiple programs connecting NYCU with IIT Bombay, IIT Delhi, IIT Kanpur, and IIT Madras for the joint and dual degree program, along with industry partners like TSMC, MediaTek, Micron, Wistron, Delta Electronics, and several others. He was instrumental in setting up of International College of Semiconductor Technology at NYCU, along with Vice President NCYU, Professor Edward Chang, and President NYCU, Professor M.F. Chang, under the guidance of Professor Jack Soon, who was ex-CTO of TSMC during the year 2015 to 2018. Under this college, 40 students from several IITs were able to visit Taiwan for their joint or dual degree and work closely with the industry. Very impressive profile, Sankalp sir. I must say, truly honored we are to have you today with us.
Thank you, ma'am.
And dear participants, I would just like you to draw your attention to this, that his major task has been to bridge the gap between the industry and the academia, which is all we are very much looking forward to. So I just hope that when question answer begins or whenever the session or time permits, we should all be taking the maximum benefit, the advantage out of it in order to be able to provide the same benefits, extend that to our students, right? So yes, handing over to you, Sankalp sir.
Thank you, ma'am. Thank you for a very warm introduction. Uh, and I have been given a topic overview on recent trend in VLSI for academia. But I have just kept it similar. But I also wanted to add opportunities for student and even for faculties, right? So, which will add another flavor to not make my presentation a monotonous one. So,
That's great, sir. That's
thank you,
great,
ma'am.
sir.
Yeah. So, good evening, everyone. I am Dr. Sankalp Singh. I am University Program Manager for Synopsys. And today, my talk is on insights into semiconductor or VLSI technologies. What are the trends and what are different opportunities existing right now or in future, keeping in mind India as a center place. Okay. So, before I start, I would like to tell participant that I want to make it more like a dialogue, right? So I would be encouraging anyone asking me questions. If you don't understand anything, because this is a generic topic, uh, feel free to ask. I'll try to keep it as simple as possible so that everyone understand what we will be talking about today, right? So the agenda for my talk is divided into three major topics. One is the technology and trends. Second is what are the department which are in focus. And third one, especially for students and faculties, what it takes to get one position in this industry, right? So let's get started. Uh, so if you see in today's world, it is not just electronics which is driving the microelectronics or the nanoelectronics or the VLSI trend, right? Uh, the things have evolved in such a way that the adjacent sectors. Yes, any questions? Okay. So the adjacent sectors are becoming more and more electronic or chip heavy. And because of that, what has happened? A lot of new challenges are coming. And as a VLSI or a semiconductor professional, we are working in this area to resolve whatever challenges we are coming across, right? And if you see, be it the mechanical sector, be it the finance sector, be it the automotive sector, be it the AR, VR, anything to do with high data centers, right? And not just the traditional chip design, satellites, right? We are evolving in such a way that I'll say on a daily basis, the trends are changing, new opportunities are getting created. Even for people like us who are there in industry for long time, we are seeing that we also need to improve and keep learning, right, on a daily basis so that we are following the trend. So this is just a very holistic view that you may be from any department of your engineering major, but somewhere the chips, which is part of the VLSI or electronics domain, are playing a key role, right? So, of late, you would have heard the biggest acquisition which happened in the semiconductor industry of $35 billion was Synopsys acquiring a company called Ansys, right? Synopsys traditionally being a EDA and an IP company. EDA stands for Electronic Design Automation, and now it is not just the silicon design which Synopsys wants to focus on, but they want to do the entire system, and that is where you partner with someone or you get someone on board who can help you accelerate that. So it is not just the silicon story what world is looking for, it is the entire system story which the world is looking for, and that is where Synopsys plus Ansys now we are becoming a leader, or in fact we have become a leader in providing engineering solution right from silicon to systems, right? So like I mentioned, electronics is everywhere, be it memory, be it gaming, be it 5G, be it automotive, AR, VR, financial sectors, space sector, HPCs, data centers, you name it, there is some piece of electronics which is available, right? So, because of this, the demand is evolving. Everyone wants to have, we say it like smart everything, making it much more smarter, right? And because of that, what is happening? A lot of new innovations are happening, and semiconductor is helping drive that innovation. And all these innovations, like when we talk about the system story, is a mixture or a fusion of lot of data, lot of compute, lot of machine learning, lot of intelligence going together, right? So if I have to give an analogy, right, of chip fabrication, I always use this analogy, and I have been using it for several years now. It is like someone who wants to write their own book, right? So, what all they need to do. So, as an author, if I want to write a book, I will go have a contract with some printing press. Printing press will go and buy raw material, buy the equipments, do the printing for me. Once I say, yes, this is turning out good, the draft is good, then they are able to go and print millions of copies, right? So, same thing happens in chip fabrication, right? Like an author writes a book, here a chip design engineer write the layout or the codes, and for that they use the EDA tool, right? Then these engineers they go and work for some specific area. So, right, like an author, I can write a comedy book, I can write a fiction. I can have my own genre, right? I can have a novel, I can have a historic books or whatever, right? So I'll have my own genre. Similarly, for the chip, it can be for any end application. It can have their own genre, right? Once it is finalized, I go to a fab. Fab is just like a printing press. Once I complete my agreement with them, they go and buy the silicon, they buy the chemicals which are used, they buy the special gases which will be required. Then they go ahead and procure their own equipments, right? Once the process starts, right, they start to manufacture it. And once they see that the first test case is coming out good, it is tested, all the testing, characterization, whatever required is done, and the chip is working fine, then they go ahead and print millions of copies of that, right? So it is something similar to printing a book, right? For a very layman language, right? So, like I mentioned, semiconductor chips are used in almost everything these days. Earlier, it used to be computer, cellular phones, iPads. Now it is going leaps and bounds. They are increasing their own sectors, right? And the usage is not limited anymore, right? So if I have to just take a simple example, right, of a mobile platform, uh, if I open any of the latest and greatest Android phone which is available in market, or say an Apple phone which is available in market, they will have their own processor. Very few companies are doing that, right? And if you see, if I just need to be a part of that processor design group, I have multiple roles as part of my career opportunities, right? So if I break open this, this is how a mobile SoC will look like, right? So there are so many modules which goes inside. Each module have their role to play. Then there are IPs, the peripherals, right? Then there is a, communication thing which is available. Then there are audio, headset, speakers, amplifiers, other component. Then there is a battery, and all those things are connected to the core processor using some peripheral IP or some niche IP which is required. Say, for example, it can be a USB IP, it can be a AMBA IP, or it can be an I2C or UART, right? So all those things come together. That is how your simple uh, processor or a SoC for a mobile is built, right? Even though it looks so simple from outside, but inside there are lot of things which goes as part of reinventing or re-engineering of all these different components, right? So, like I mentioned, uh, as one analogy, so there are phases for a chip design or a IC design, right? First thing is you want to specify what will be the use case of that. I want to use it for some, say, 5G application. I need a uh, this much frequency, this much bandwidth in which it should work, right? This much noise should be there. If it is beyond that, it is no good. If it is less than that, it is good. What is the bit it can process? How much data it can process? All those things you will have to jot it down. Based on that specification, you start your design process. Design process is again, once you decide what you want to build on, you start your process. Then you do your RTL coding, or if it is on the analog side, you do your layout, you do your schematics. Uh, Once everything is fine, once the GDS is ready, you go and give it to a fab where the entire manufacturing process starts. Once the manufacturing is done, then it is assembled, it is tested, it is packaged, and if everything is working fine, it is characterized. Then millions of copies of that comes out in market, right? So this is how the phases for IC design happens. So if I have to say how the ecosystem looks like, right? Ecosystem of semiconductor is means like it cannot be independently operating. Everything is interdependent. So if you see the bottom of the pyramid, these are the companies who provide IP cores, right? Then there are companies on the next level. I'm going from bottom to top, right? And these are only three companies right now who do provide EDA tools, Synopsys being one of them. Then there are companies who only provide specialty chemicals and gases, the materials which will be required for doing your chip design thing. Then there are companies who specialize in providing equipments. Say, for example, ASML, which is based out of Netherlands. They are the pioneers in sub 3 nanometer lithography equipments, right? Then on the left hand side, there are companies who are called as design houses, the multinationals like IBM, Nvidia, Broadcom. Any questions? Uh, any questions from the audience? Okay, no. Okay, so these are the multinationals which are also called as fabless chip companies. Then there are companies who have their own fab as well. These are called as integrated device manufacturing things, or the IDMs. Say, for example, Samsung, Intel, Micron. They do their own design, they do their own fabrication. And then there are foundries, say UMC, SMIC, TSMC, Global Foundries, and others who actually do the manufacturing for fabless and IDMs, right? And beyond that spectrum, that they also have the OSATs, the ATMPs, the system companies who uses that chip, right? So if you see in India's context, right from bottom to top, apart from the topmost part of the pyramid, everything else is having a presence in India. Even though global foundries have a presence in India, but it is not a fab. But it is more on the fabless side of it. Tata is setting up a fab in Gujarat, right? Tata has already set up the OSAT and the ATMP facility in Assam. Micron is setting up a unit in Gujarat. Keynes is setting up. So these are the companies who will be doing the OSATs and the ATMPs. And because the chip will be coming out locally, there are already a lot of system companies who will be using these chips. Say, for example, if you see Tata's case, Tata Motor is already interested to use the chip which will be manufactured by Tata, right? So if you see the semiconductor landscape, it is going from bottom to top now, as part of the list which was mentioned in my previous slide. There are system houses like Nokia, Apple, Cisco. There are IP vendors like Synopsys, ARM, Cadence. There are design houses. There are EDA vendors. There are ASIC manufacturers, and then there are memory devices companies. So whatever you see in purple here in this slide, these are actually a job profile, right? So you can be a simulation guy, you can be a standard cell development guy, you can be a backend guy doing the floor planning, you can be a static timing analysis guy, you can be a system integrator, you can be a chip architect or a system architect. So all these things, and these companies which are bucketing these things do have lot and lot of requirement for these roles, right? So another way of looking at things, if you want to see, I have listed five major verticals, and inside that, whatever you see as sub points, these are more or less a job profiles, right? I have just kept it in such a way that whatever you will be studying as part of your VLSI or electronics courses, you will come across with all these terminologies, and these terminologies are basically one or the two job roles available right now in India. So you can be a chip validation engineer, you can be a DFT guy, you can be a process package guy once the fab is up, you can be a design guy doing specialty things, right? You can be a simple application engineers who concentrate on different part of it, right? Again, it can be EDA specific, it can be IP specific, it can be system specific. So whatever you think of, all those things are part of the job market. Another way, which is what students generally know right now, is you can be a verification engineer, a front end guy, you can be a implementation engineer, a back end guy, you can be a DFT guy, you can be an analysis guy, right? Where you're doing your package, thermal analysis, and other thing. You can be a logic designer. Uh, so these are some of the key areas or terminologies which are relevant or prevalent in market around chip design, and all those things do lot of different things inside as part of that particular role. So if suppose I am a backend guy, I am a PD guy or an implementation guy, I may be doing sign offs, I may be just helping do your synthesis and place and route. I'm not sure yesterday if you would have got an insight from Karan Shah. He is a PD guy. He is an implementation guy, right? His major work is to do all the place and route, site synthesis, sign offs, another thing. The speaker who is after me, Ashlesha, she is also from the same domain. And their role is to help customers who are actually doing a chip design to make sure that the sign offs are done properly or the synthesis, place and route is done properly, right? Uh, so if you see what is happening right now, like I mentioned, everywhere the demand for chips is increasing, right? Every sector is getting influenced by semiconductor chips. So trends have also started to change. So if I see, people used to think that if I know how to write an RTL code or a Verilog program, I can have a say in the chip design industry, because that was morely driven by softwares, and everything which was getting realized in real terms, it was because of the chips which were designed using those software. But now the new trend is how do you optimize your software so that whatever chip you are building, that will help you to build that system story which you want to have, right? So because system need to be very safe, system need to be secure, system need to be reliable. It cannot be that I may be a very good software guy who is doing the RTL programming, I may be a good foundry guy who is building your chip, but if that is not giving me the best performance, it is not secure, it is not reliable, then it becomes a major challenge, right? So from software to silicon, silicon to systems. This is how the trends are changing, right? So if you see on the software driven thing, you will see certain brands which are highlighted here. Uh, they are also getting influenced, right? And new companies are coming up in this space, And when I say in this space, it is not that they are going and doing the RTL programming or they are designing a chip, but they are becoming an end user of that chip, which is actually helping them. So, for example, I have mentioned Starbucks or say Johnson and Johnson or Caterpillar, right? Uh, what they are trying to do is they are trying to digitize their entire supply chain. They're trying to have their own digital twin solutions, right? And for all those things you need softwares, right? And if you see, because of all these things, uh, their efficiencies have gone multifold up, right? uh, and same way you will see the traditional players who are doing chip design. They are not just limiting their themselves into that, but the new entrants are coming into that. So, say for example, automotive is a best case. Post pandemic in 2020, we saw a huge chip shortage, and because of that, a lot of vehicle deliveries were not able to be done on time, right? A lot of multinationals who were traditionally or IT companies in the past, they started getting involved. They want to have their own chip, they want to have their own SoC, they want to have their own cloud setup. So everyone wanted to have their own chip, right? So that became a very important learning or a lesson where the traditional players were not just doing the things, but the legacy player who were not from this sector, but from the adjacencies, they started jumping into this. And because of that, what happened? Uh, People started to get the best optimized software, right? So if you see Apple, uh, if I recollect properly, somewhere around 2017, 2018, they said we will have our own processor in the MacBook, which was having M1, M2, M3 series, and so on, right? Traditionally, they used to get their processor and everything was from Intel, which used to come in. Now they said, no, we want to, because Apple was more into the hardware, the and the software associated to that. But now they said, no, it will not be just the hardware and the software, but it will be a mixture of that, so that when I build a finished product, I will have more control, I will have more options to optimize things, right? Same way, traditional fabless companies like Qualcomm, they started partnering up with Microsofts of the world, wanted to have the best AR VR solutions. Tesla is the best example. Tesla started with more on building smart cars, which was powered by EV, right? Then they said, no, it will be fully self-driven cars, and for that you need to have your own chip. So they started designing their own chip so that tomorrow when they go from level 1 to level 2 to level 3 or whatever on their autonomous driving thing, they can optimize it much more better, right? And at the same time, companies like Intel, who were doing their own design, who were manufacturing their own chip, right? They started pivoting and said it will not be just the software first approach, but they also want to have the entire architecture built by themselves, designed by themselves for their hardware. So that is how the trends are evolving, and this we see that this will continue for long, right? So if you see how the market verticals are changing, I have just taken some snippets here, and it is right from silicon to software, right? Journey, if I have to say, the mobile, the 5G, HPC, that is becoming more and more mature towards silicon, and a lot of people want to have their own silicon, their own hardware. It is not just limited to the software or someone doing their system or design, but at the same time, other verticals, which is automation, industrial, financial, they are doing lot more designs now. They are moving away from the software side of it, getting into the system story, and eventually they will be getting into their own silicon. So, and for all these things to happen, synopsis plays a very important role in their entire journey, right? So, what is happening in India? India also, we say that India missed a bus almost like 20 years uh, now. Actually, it started somewhere in 1985, where we came up with SCL, then some accident happened, it got delayed. Then again from early 2000 to now, if we see in last 20, 23, 25 years, uh, we are still stuck at 180 nanometer, right? And so Indian government after pandemic realized that they need to pump in money, they need to build infra, they need to build the ecosystem, they need to build the yes.
Carol ma'am, please mute your mic.
Okay. So what has happened? A semiconductor mission for India was launched. It was announced by Government of India in 2023. At the same time, Ministry of Electronics started working with IBM, CDAC on semiconductors, AI, quantum missions. AICT got involved in curriculum for academia. They started revisiting on the curriculum. They launched a new UG and PG diploma program in VLSI. So it's a collaborative effort which is going on, and at the same time, industry players which were having or MNCs which were having their presence in India, they started being a part of this journey. So now there are multiple programs which are going on under India Semiconductor Mission. There is a chip to startup program. There is a design link incentive for startup. There is a production link incentives. There is because of all these things, a fab is coming up. OSATs are coming up in India, right? Uh, how we are working with academia as synopsis, right? So we are working with government, we are working with industry, we are working with universities. We have started multiple collaborations. Say for example, we have partnered with IIT Bombay, we have partnered with IISc Bangalore, we have partnered with BITS Pilani. We have a program called SARA, which is Synopsis Academic Research Alliances, in last 5 years. I drive that for India, right? And we the workforce development becomes one of the key goal of SARA, along with all the other partnership models, right? So, what are the skills required, and which are the engineering or the discipline which will be required? Is of course, if you see the first discipline which comes in mind is electronics, diploma in IC manufacturing, BTech, whatever programs we have been doing. Now there is a BTech VLSI program, MTech VLSI microelectronics is already there. Computer science, because of traditional CS and IT, is evolving. They are getting into this space because of AI, ML, big data coming up big time in last 4 5 years. Material science has become a very important domain because uh, beyond silicon there are so many other different materials which are used, right? And also on the packaging side of it, lot of new materials have been explored, so this becomes one of the key area for doing your research if required in academia. Mechanical is again back. A lot of people from instrumentation, robotics, industrial, automation, production, they are getting a pent up demand because of the fabs and the OSATs which are setting up here, right? Biotechnology is one area which is also now becoming more relevant, especially bioinformatics and bioengineering. And because of the new drug discovery, you need to do a lot of iterations on the simulation world so that before you actually go and build some composition, you are at least sure that this composition, whatever you're building, will work. And then you go ahead and do a lot of trials and make sure that things happen. This is a biggest example in recent 5 years post pandemic, that how quickly people were able to come up with vaccines so that they were able to make sure that this spread is not there for a very long time. Chemical engineering is also in demand because of a lot of specialty chemicals or gases being used. And also, again, for the packaging material, a lot of chemical engineers are required to build new set of materials, right? And the domain which especially India neglected for a very long time, that was basic sciences, where we had people doing BSc in physics, chemistry, mathematics, but not seeing uh, industry where to get into. And they continue to do their BSc, MSc, PhD, and then get into academia as one career option. Now they are being looked after by a lot of people in Fab because they play a very important role uh, in this entire ecosystem, right? So if you see, like I mentioned about the system to silicon thing, how are different manufacturing roles getting evolved, right? So I have just taken some snippets from the past uh, when I was building on this material. The traditional companies, like I mentioned before, are looking into adjacencies. So, for example, we know Meta X name was Facebook, was a software company, right? An IT company. Now they are looking for advanced material researcher because they want to have their own chip so that because of that they can make sure that using whatever CPUs and GPUs tomorrow, they will be able to have much more wider thing. Plus, they want to have their own silicon. At the same time, Google, again a software company, are now having a good sizable team in India, plus in US who wants to do packaging. They want to have their guys focusing more on chip design. Traditional companies like General Motors, more into automotive, want to have a wafer fabrication procurement guy because they want to have the best quality of wafer so that whatever will be used, that will be beneficial for their cars. At the same time, Qualcomm, which was a fabless company, is now looking for a foundry engineer because it cannot be just one way of seeing things. You also need a lot of inputs from foundry. So they are looking for people who have experience in foundry and they can actually help them optimize their designs, right? So this is a current scenario and this is also evolving. So coming to the last part of my talk, what's in it for me, right? If I'm a student, if I'm a faculty who want to make my career advance in semiconductor or VLSI space, what I need to do, right? This is a very common question which I get whenever I visit any academic institution by students, by faculties. So let me just put some five, six key bullet points which I have realized. First thing is you need to have a very strong basic, right? And you need to upskill yourself. You need to not just limit yourself on the theory side of it, but you need to do lot and lot of practical experiments, right? Whatever lab opportunities you get, make the best use of that. In our language, we say getting your hands dirty, right? The more you practice, more you understand things in detail, more employable you become in the market. That is what I can say. With a very strong basic. If your basics are not that great, please work on that. Second is you need to always focus on adjacent technologies. So suppose I am from BTech ECE department. Uh, but I should be open to learn, say, not just C, C++ programming, but computer architecture, because computer architecture forms a backbone for your SoC architecture, right? I should be learning Python programming. That will help me moving into the AI HPC world going forward. If I am from computer science, and I'm learning a lot of C, C++, Java, data structure. Uh, you can also go and learn HDL programming, right? Which is Verilog and other thing. Uh, it will make sense for you, right? You can at least get a design verification engineer role or whatever if you want to venture into this domain, right? You need to be connected, right? The it is said that your network is your net worth, right? You need to have good mentors. You need to, if you want to venture into this domain, you need to make sure that you are meeting a lot of people who are actually working in this area. Uh, don't feel shy asking questions. If you think it's a very basic question, uh, don't feel shy. Please ask. This will actually help you accelerate your journey in getting right kind of opportunities, right? Plus, you need to track what are the trends, how different governments of the world, different countries are coming up. There is a CHIPS Act in US. There is a Euro practice going on in Europe. There is a Taiwan's uh, Act. There is a India Semiconductor mission. There is a Japanese mission. There is a Korean mission, right? Uh, Singapore is working with India. Singapore is working with Vietnam. Vietnam is again coming up big time in manufacturing, right? So different trends are changing. You need to always be connected if you want to get into this area. You need to be a team player, right? You cannot just say that, hey, I know entire chip design flow, say RTL to GDS if I'm a digital engineer, or say schematic to GDS if I'm an analog mixed signal guy, uh, right? But if you're not a team player, like you saw, Qualcomm was looking for a foundry guy. You may not be able to interact tomorrow as part of the company's requirement, and you always need to be open for change. This will happen. A lot of things will be agile. You need to be agile in nature, adapt to that, and then start working. And if you think that these all things doesn't make sense to you, don't want to get into industry, but you want to get into academia, define your career in research, talk to your professors, do PhD, right? And if you want to pursue your ambition in doing becoming the best scientist or the best researcher, that is another option which is available. So with this, I would like to end my talk, and I will be very happy to take questions as part of this. Thank you, everyone. So, any questions from the audience?
Actually, Sankalp sir had already conveyed us prior to it that he would be briefing us everything, and then he would be open for the questions. We should take more advantage of the question answer session, because that way we can get enriched and we can sort out what are our queries and our students can get benefit.
Sure.
Yeah,
Don't
so the platform is
don't
open
think.
for all,
Yeah.
please.
Don't think your question
Hello.
is a very silly question. Feel free to ask. You can raise your hand if you want.
Yeah, please.
Hello.
Yes,
Hello. Good
someone is
evening.
trying to say
Am I
yes.
Yes,
am I
please.
audible now? Okay. Sir, I would like to ask you a question, which is regarding the challenges while designing any IP.
Hmm.
What are the challenges? What are the challenges you face while you design any IP? For example, if I want to design a digital IP at that time, what you need? What are the challenges, as well as analog IP?
Okay. So I'll not put challenges up front. I'll give you a different perspective to that, right? Uh, let's say I'm not putting it on a digital IP or an analog IP. Okay. I'm just taking a product name, right? And
Okay.
okay, and couple of products. Let's see, and you yourself will uh, understand how interesting it becomes. Okay, I'll take 2 cases. One is USB, and one is, let's say, 5G. Okay, 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 Uh, Apart from USB, let's take a very simple, okay, PCI. Okay, you would have heard these names.
Yes, sir.
USB, you have heard, right?
Yup,
USB
yup.
A, USB C, all those things you have heard, right?
Yes, sir.
The cable connectors, what we use for charging our phones, laptop, it is Type C, Type A, and all those things, right?
Yes,
So before getting into the detail on the challenges, right? Uh, if I have to just give you one simple uh, thing, right? If you remember, there used to be micro USB thing which came very early days, right? And then it became a bigger USB A to USB C thing, right? And then it became a USB C to USB C thing going on. Can you tell me what changed from a simple USB A, a bigger, broader one, to a USB C? Any simple aspect, not going into multiple aspect?
actually,
What
it's
changed?
reduced its size
Uh, Forget about the
and its
physical side of it. In terms
okay,
of
fine.
usage, right? In terms of usage, I give you two connectors. One is a USB-C connector and a USB-A connector, the normal pen drive which used to come early days, right? The USB-A, the broader one, and a USB-C. Uh, what changed in, not just in the physical size and the appearance, but what changed internally? Do you think that the speed changed of data transfer?
Yes, yes,
Huh? Can I take
yes, sir.
speed as one of the very elementary thing which you think that it has changed?
Yes,
Okay. Second thing, I give you uh say the first generation Samsung Note device, right? And today's generation S25 Ultra, right? Both of them had USB connector. Uh, Do you think that apart from speed, something else has changed in that USB, which came say in say early 2010s and 11s to now in 2024, 2025? Apart from speed, something else changed. Say, for example, the charging speed,
yes,
right? Okay, another way of looking at it. How many of you have experienced, say, the Oppos, the OnePlus, the super fast charging, or they say Whoop charging, right? How many of you have seen those ads some 5, 6, 7, 8 years back where they used to say 50% charge in 30 minutes? Now most of them are saying 50, 80, 60% charge in 30 minutes. So charging speed has increased, right?
yes,
Uh, Keeping it
yes,
very simple, USB is still USB, right? The IP
yes,
still is the same IP, right?
yeah,
Uh, Not going by the physical dimension and all those things. Just the standard has changed from USB A to B to C. And because of that, you see very basic two things. One is your charging of your phones and laptops have changed. The speed of data transfer has changed. Now, think what would have happened inside to do that. A lot of uh, architectural changes would have happened, right? Some and I'm not categorizing it into digital and analog, right? I'm just keeping it on a very elementary level. Something they would have done that because of that, all these evolutions are happening, right? So if you see from that point of view, you see that in last 10, 15 years, a lot of things have changed just in a simple USB IP. Now, if I say any other IP, right? The PCI IP, which I said, uh, again, uh, even before getting into PCIe, if you would have seen or if you would have heard from uh, people who have been using early day laptops, the compacts and the HPs of the world, now to the latest and greatest, be the latest MacBook or the Dell or the HPs, right? Uh, in that phase also, right, a lot of things have changed. And there it can be the HDMI, which is again an IP. HDMI IP has changed. Bluetooth, for example. I still remember using Nokia's not the touch one, but the button phones, which had Bluetooth thing, and you need to bring two phones together along with the infrared. There will be a port, and then try to make sure that your Bluetooth is getting paired. It cannot be at a very farther distance. But now, if you see on just on the Bluetooth side of it, uh, we get a very good range, right? It is not just the traditional 1 meter, 2 meter, 5 meter kind of a thing. We are now getting even say 50, 60 meter of range. So just to do that, Bluetooth IP still remain Bluetooth IP, but just to do that, a lot of things get changed in the background. And like you mentioned, that is where the complication starts. Other way of seeing at it is more number of transistors getting added, right? Different designs coming up, different architecture coming up. Because of that, again, things are changing. So uh, I hope I was able to articulate it in a very simple way for you.
Yes.
Okay. Any other questions?
Sir, good evening. This is Dr. Anandan.
Yes. Good evening.
Sir, what are the job opportunities are there for basic science students, sir, in this regard? Or what are the courses are available to equip them to become I mean, entering into the semiconductor industry? Can you
Okay.
explain, please?
Okay. So when you say basic sciences, I mean you are meaning with physics, chemistry, mathematics, guys, right?
Yes, sir.
Okay, okay, got it. So, like I showed in my slide, right? So generally what used to happen, I'll take physics as an example. People used to do BSc physics, then they used to do MSc physics. Now people have started doing applied physics, right? Then they used to, some people wanted to get into teaching and doing research, they used to go and do PhDs and all, right? But now what we are seeing, lot of people who come with say mathematics and physics background, they are very good in problem solving, they are very good in equations. Just to give you an example, when I was in Taiwan, I hired a BSc, no, not BSc, MSc mathematics guy, right, who was doing a master's in India, and got him as an intern first in Taiwan for 6 months, and then later on he went ahead and finished his PhD. Was these students were very good in solving bigger equations, which used to go in robotic arms. It used to get into the EM and all those things. So we were able to get two different, entirely opposite spectrum uh, areas. One was on the robotic arm for the industrial side of it. Second one was for EMIR, especially for your magnetic or wireless power transfer. So these guys become very important. And if you see trends happening in India, a lot of people after finishing their MSc, they go ahead and do MTech in some adjacency area. Say, for example, I have a friend who did his uh, MSc from BHU, and then he went to do his material science MTech from IIT Bombay, and now he is working for TSMC. He is a material guy because he was coming from physics, he pivoted into material, applied physics, and then into material. So it became a career pathway for that. And there is a huge demand for these guys right now. So this is one way of seeing things, especially with basic sciences. Also, on the biology side of it, it is not just the traditional botany, zoology which is required, but someone with more uh, bioinformatics, genetic engineering. These are again your BSc, MSc areas. They are getting into semiconductor industry, especially for uh, along with the chemical engineering guys for helping them with wastewater treatment, acid which is used to make sure that it doesn't pollute, more towards the environmental side of it. So that is another career pathway.
Thank you, sir.
Yes. Yes. Someone has raised their hand. Yeah, Devendra Singh, please go ahead. Please unmute yourself.
Yes, Mr. Devendra Singh, you can unmute yourself and then you can ask. Okay.
Deepika, if Devendra is not
Yes,
asking.
Deepika.
Uh,
Meanwhile, we can take a question of Deepika. Yes, Deepika.
Good evening, sir. My question is, what are the opportunities for diploma engineers who are doing diploma in electronics and communication?
Okay. So right now, are you doing diploma?
I'm a faculty of diploma students.
Okay, so ma'am, very good question, a very important question. Right now, if you see when a fab will be up and running, say Tata's fab, right? We are all anticipating that by 2028 we may have the first chip coming out from India, from Tata's fab. Uh, so if you see a fab, if they want to run a fab, there will be a team who will be doing the design. There will be a team who will be doing a lot of equipment handling and all those things. But there will be a lot of people required on the shop floor. We say it a shop floor where actually someone will be making sure that all the test characterization processes required, uh, which say for example someone needs to do lithography, then they need to do etching for example, or they need to do annealing. So these are the guys, the diploma guys, who are required in huge quantity as compared to engineering guys in a fab. So with fab coming up, diploma becomes a no-brainer. With OSATs coming up or already being up and running, lot of diploma guys. So just to give you an example, Tata has their facility closer to Bangalore. There is a place on Tamil Nadu Karnataka border near Hosur and Bangalore, where they have actually bought a old facility of Wistron, which used to manufacture iPhones, do the assembly of that. So what these guys are doing right now, anyone and everyone who is around that area, especially females, say 50 to 60 kilometers, uh, and having some diploma in electronics or some other background, they are become the most demanded people, because they are the one who is actually doing the testing side of it. Because if you see traditionally, uh, a diploma guy vis-a-vis an engineering guy, diploma guys are more hands-on, right? So their demand is
Yes,
huge, and that will continue to happen with more fabs and OSATs and ATMPs coming in India. So huge demand. I see a bright future for them. In fact, there is a diploma in IC manufacturing approved by AICT already.
yes, sir. Thank you, sir.
Thank you. Yes, Devendra. Now, if you are okay to ask question. If not, then Himanshu. You can type your question,
Yes, sir.
Devendra Singh.
Yes, sir. I'm audible.
Yes. Himanshu, please go ahead.
Sir, uh, can you list the research area where students have to work on semiconductor sites?
Sir, any area if you think in this domain, like I mentioned, right?
Or engineering background students?
Yeah, any area if you think, right? From my talk, everything can be a part of the research thing, but the only challenge is, do you really get people? So, for example, uh, you can do research in the design. You can do the research in AI integration into, say, verification, AI integration into physical design, uh, right? You can have people doing research at device level. You can have people doing research at material level. A lot of people working on, say, not just silicon, but say silicon carbide, gallium nitride, gallium arsenide, traditional materials. Now they're talking about uh, 2D materials, the graphenes, the molybdenum disulfide, tungsten diselenides, right? So anything in the material domain. People doing research on making new chemicals, because chemical is very expensive, especially in the semiconductor fab domain. People doing research uh, in, say, creating some next generation chip for, say, HPCs, or uh, say 5G moving to 6G. Uh, so means you can name it any area. If you think, there are a lot of opportunities in terms of research.
Okay, thank you, sir.
Yes. Next, Miss Harsha.
And Devendra, are you there? Okay, Miss Harsha.
Hello. Hello, sir. I would like to ask you one question, which is regarding layout designing. Uh, can we still apply for lambda and lambda rule while designing layout of chip?
Traditionally, yes. Uh,
Okay.
Depending on what uh, chip or problem statement you're working on, answer may be a no.
Hmm.
But basic answer is a yes.
Okay. Actually, now we are going to use all artificial AI tools and all this stuff. Actually, I want to know whether we are going to use that rule or not.
Yeah. You see anything, right? Uh, so first
Mm-hmm.
thing, I would like to clarify, anything, whatever we say that with AI integration and this and that, your basics physics will not change.
Okay, fine.
Okay. Ohm's law will still remain Ohm's law.
Yes,
I'll
yes. Yes.
put it that simple. V equal to
Yeah.
IR, you say, I say, or tomorrow a agentic AI or an engine says, it will still remain V equal to IR.
Okay. Actually,
Okay,
I was confused about.
yeah, so it will not
Thank you so
change.
much.
So all these AI thing, whatever is getting, it is helping us increase our efficiency. I'll just say that it is
Okay.
an aid which is helping a chip designer or an engineer to improve their efficiency, improve their uh, work timing. That if I was able to write a code in, say, uh, 2 hours, now I can write a code in, say, 2 minutes, 2.5 minutes, 3 minutes, right? I
That's
just need to give my specs, the whatever uh, Copilot or Chat GPT or whatever I'm using, right? It will
mm-hmm.
throw me tons and tons of data. So that is only helping me out. So the four lambda rule will still be there. So you don't have to worry about that. AI will not change it to any other number.
Yes, yes. Thank you, sir.
Yeah. Okay. Thank you. Yes, Ashish. Ashish, you can mute yourself and ask question.
Okay. Is this audible?
Yes, Ashish. Please go ahead.
Yeah, this is Professor Ashish calling you from Faridabad. Faridabad, Delhi. Faridabad, Haryana. Hello.
Yes, yes, sir. Please go ahead.
Yeah. I was just asking about this processing. That generally that the chip makers now feel that the silicon is off days. Now the silicon wafers is replaced by gallium nitride, right?
Hmm.
So and silicon vapors sometime it displays the toxic in the nature.
Hmm.
So, so the processing is the same. Everybody knows that they are acquainted that how the this processing semiconducting processing for the chip manufacturing they make. My question was there: is there any process or is there any idea to develop a device, the semiconducting device, through the additive manufacturing 3D printing technology? Is there any
Uh,
idea or any research is going on?
okay. So let me come one by one. Silicon was there, is there, will be there.
Yes,
Okay. Depending on what application I want to work on, I may pivot into gallium nitride.
yes,
Gallium
correct,
nitride
correct, correct.
can't help me get what I can get it on silicon. Still, the next 3 to 1.8, 1.4 nanometer devices are being built on silicon, right?
Yes.
So whatever we may say, silicon is there to stay. Depending on application, say a 5G to 6G or a high voltage application, silicon to
Hmm,
silicon carbide or germanium
hmm,
or gallium nitride,
hmm, hmm,
yes,
hmm, hmm,
there are options. Coming to your additive manufacturing side of it, 3D printing, especially on the chip design side of it, it will not be like the similar process how we actually do it in a fab, right?
hmm,
Say for
hmm.
example, I may not be doing a lithography, etching, annealing, whatever the
Yeah,
depositions and all
the
those things,
oxidation and all. Yes, yes.
right? That I will
Yeah.
not be changing, but I may be using additive manufacturing to help build when we are doing an assembly, right? I may be using an additive manufacturing at some other stage, but I will not change the basic CMOS fabrication steps or replace it from traditional steps to additive manufacturing thing. I can use
Mm,
it. I can use it. Once the chip is ready, I can take that chip out, put it on a PCB. I can design a PCB using a 3D printer, right?
hmm, hmm,
I can do that, but I cannot design a chip directly. Say a silicon chip, a silicon simple MOSFET, uh, any tech node, say 180 nanometer, right? I will not be able to do a chip directly using a 3D printer. But I may use the peripherals or the other things which we used to traditionally do it in a different way through additive manufacturing or 3D printing technique.
correct. Yes, but for the MOSFET and the CMOS, that is okay, fine. But
Hmm.
my concern was little. It was there. Okay. Thank you very much for your reply, Shankar. So my one was there the temperatures is the another factors, and during that the processing and another things even the etching and all this is so and the second things there is a losses during the processing the semiconducting for the chip manufacturing process fab process some losses are observed. So this if we use that the 3D printing there may be the zero loss or net losses is zero. So that's why, is there any, was there any idea to do this is
No, no,
anyway,
no,
thank you very much.
no. Yeah, no. If it is for the chip or the MOSFET or CMOS, answer is no. But yes, for the other things, answer is a yes.
Okay, okay, yes. Thank you very much. Thank you.
Thank you, Ashish.
Thank you, sir. Thank you.
Yeah,
Thank you.
yeah. Cynthia, you can ask.
Thank you.
Cynthia
Good
Dhanraj.
evening, sir. Uh, Good evening, sir.
Good evening.
Uh, as you told earlier, environmental engineers have also job in this field, right?
Yes, yes.
Uh, what will be their role? Will they will be try to contain the toxins that create by semiconductors, or they will be what will be their role? I want to know that
Okay.
actually.
So if you just do a simple Google search, right, and let us take TSMC, a well-known fab around the world, which has almost 90% market share. Uh,
Okay.
okay,
Hmm.
they do have a toxicity engineer role.
Ah,
Okay, so that
yeah.
person's only role is to make sure that because when I am doing an actual fabrication in fab, right,
Hmm.
I'm using say HF solution, I am using Piranha solution, I'm using n number of different chemicals in different compositions, right?
Hmm.
Uh, so uh, do you think that if I just take H2SO4 and just
Okay.
pour it on a silicon wafer and then that poured H2SO4 is going down the drain, uh, will it not increase the toxicity level? The answer is yes. So there are process SOPs in place so that if I want to actually do a cleaning of a simple wafer using some chemical, right? H2SO4
Yeah.
being one of the well-known name, right?
Yeah.
I'm just using that as an analogy. So there are
Okay.
guidelines laid to that that if I want to clean my wafer with this particular uh, solution, I need to follow A, B, C, D, E, F, G. These are the steps. If I want to use it for some other chemical and then I have to discard that thing out, there are ways how I need to do it. So for any of these fab and all those things, uh, there is a huge demand now with all these green buildings, this and that and all going on, right? The
Yes.
ISO's regulation becoming more and more stricter. Uh,
Yes.
so lot of people coming up from environmental engineering, a lot of people coming from genetic engineering pivoting into this area are being looked or sought after. So that's how I see one key area. Then if you see all these plants, they recycle a lot of water because
Okay.
this fabrication thing is water, means huge amount of water is required,
Yeah.
right? And if you see countries, or even if you say tomorrow the fab which is coming up in India, it is coming in the state of Gujarat,
Hmm.
right? And traditionally, Gujarat is not a state which has abundance of water, say
Hmm.
as compared to say Punjabs or the Uttarakhonds where the Ganga comes out and all, right? So you will
Hello.
require lot of recycling of water, reusage of that. Again, you will need these guys who will actually tell people how do you do this thing. So there are actual job profiles in fabs and all these places where they look for people with all these kind of backgrounds.
Thank you, sir. Thank you.
Thank you, Cynthia. Yes, Dr. Shweta.
Good evening, sir.
Good evening, ma'am.
Is there a specific government or private initiative supporting VLSI research in India?
Yes, ma'am. There are a lot of them. There are a lot of them right now. So there is a Chips to Startup program, which came out early 2023, where the original call for proposal was uh, to do actual chip, right? And it was all R&D oriented. The category one had funding of 5 crores. Category two, where minimum three, maximum five college needs to come together and form a cohort, was 96 lakh for each college. So that's roughly 3 crores to 5 crores if I have a team of three and a five college coming together. Category three was 86 lakh. So that's a best example I can put forward. That scheme is going on right now and it is active till 2028. But right now, government is not doing a funded project there, but they are enabling colleges to get EDA access for workforce development for classroom teaching. That is one. DST with ANRF have already announced a lot of schemes where, especially on semiconductor and other deep tech and high research area things. RDI being a latest announcement by government, where government has earmarked 1 lakh crore for next 10 years, right? So then you see different schemes going on by different T hubs available with IITs or at the state level. They have their own schemes going on. So there are a lot of schemes going on right now, ma'am. It's very easy to reach out to all these entities, and if your proposal is really strong, uh, you will be getting funding. And these are all things which is related to semiconductor and chip design. So, Dr. Shweta, I hope I was able to answer your question.
Dr. Shweta, are you there?
As she was on mute.
Yeah, yeah. Okay.
Okay. Any other questions?
Thank you very much, sir. Thank you very much.
Thank you, Dr. Shweta.
Anyone else? Uh, Sankalp sir, I would like to have I would like to ask a question to you.
Sure, ma'am.
Like being in Gujarat and nearer to the geographical location, which is quite nearer to Dholera plant, right?
Hmm.
How can we contribute or train our student to focus in a specific direction, right? You know, to be able for them to be able to get this or into the micron or anywhere in Dholera plant, how can they approach or how can that journey be easier for them?
Okay. So, ma'am, let's first understand at your college level what is the core competency in terms of faculties, right? Uh, do the faculty, suppose you say we have 10 faculties in semiconductor slash VLSI slash microelectronics domain, right? Uh, Suppose out of that 10, two have a background of manufacturing, two have a background of, say, devices.
Okay.
One is in digital domain, one in analog, or two in analog, whatever number, right? Then you need to take a call as a department collectively saying that let's focus on, say, if like you mentioned Micron, right? So you
Hmm.
will require people for the facility which Micron is building up near Ahmedabad, right?
Hmm.
So and same time, is that related to what Tata is building? Answer is somewhat it is similar, but not exactly the same, right? So suppose you
Okay.
say, I will focus on these two areas because these are the two key players which are setting up their operations in the state.
Hmm.
One is on the fab side of it. So two things for fab. One is on the devices, and second
Hmm.
is on the fabrication side of it. So any
Hmm.
course which require or which is available at your end right now,
Hmm.
and if you want that this needs a revamp, you can always reach out to the folks in Tata. They will be very happy to help, right?
Acha. Okay. Okay.
Second is, now you say that no, we are not worried about the Tata thing, and like I mentioned, that a lot of more requirement will be there for diploma guys.
Hmm.
Let's focus on Micron. So again, the OSATs and ATMP, the packaging thing becomes a primary thing there. Uh, so you
Okay.
can take packaging as a core area. Now you can start building things in and around that. Whatever courses are available,
Hmm.
revamp that. you
Okay.
can actually see what the latest BTech VLSI program course curriculum have been defined by AICT, right? That can give you a very good starting point, a skeleton structure, uh,
Mm-hmm.
and from that, depending on what is available at your end, right? Tomorrow it should not be that, sir, you said to do analog, but I don't have any faculty in analog.
Okay, got it.
So, depending on what is available at your end, you can start building from there, and then based on that, you can move or see as your faculty strength changes or they upskill themselves. You can always go and do the adjacencies.
Got it. Okay. Thank you.
Thank you, ma'am. Yes, Dr. Shaheen.
Uh, yes,
Yes,
Dr.
sir.
Shaheen.
Thank you. Thanks a lot, sir, for your very valuable and informative lecture. And in a very simple language, you have been able to reach to us. The point is, my question is very simple. And I am an admission engineer Haryana. The point
Sir,
is,
sir,
since the
sorry,
last
I didn't
8 to
get
10
you.
years,
Sir, sorry, I didn't get you. There was a lag.
sorry, I repeat, I
Yeah,
repeat.
please.
Actually, being an admission in charge in Mewat Engineering College, Nuh, Haryana,
Okay.
I'm asking you a simple question. Since last 8 or 10 years, I have seen the electronics seats are almost vacant. I mean,
Yes.
very few takers. The
Hmm.
point is, keeping in mind the very promising things going ahead for electronics, are we expecting on in reality the students, opting, lot of student opting for electronics in the future? Will
So,
that be a
sir,
kind of situation?
the answer to that is any domain, if you see, especially in India's point of view, right? It is cyclical in nature. I
Mhm.
remember early 2000s, uh, it was mechanical, electrical, which was dominating. Then a wave came that computer science, IT became a thing. Then a wave came, ECE became a hot thing in terms of admission. Then again, mechanical died, civil died, ECE, computer science, IT remain. ECE died, computer science remain. So what is happening? It will be cyclical in nature because at the end, if you see from students' point of view, there are two things to that. One is there is lot of pressure coming from parents that this is what you need to do. Student at that age, once they finish their school education, they are somewhere around 16 to 18 years, and major decision what they want to do is taken by parents, and that is not based on their experience, but it is based on what people are doing in and around, or what someone is doing in that village or in that town, which has come up in newspaper. A lot of decisions get influenced that way. So because of that, what happens? Students are forced into something which is not their primary area of interest. So then at one point of time, they lose interest in that, right? You can be a best in best college doing computer science engineering, but if you are not interested, uh, you may still not be going ahead and doing building a career around that. I know many people. In fact, I myself can say that if you see my profile, I'm a BTech EC, master's in nanoelectronics, PhD in material science, and then postdoctorate in high power devices. So it's a complete different trajectory uh, because trends kept changing and I kept following that. Uh, I was blessed that I got good mentors who gave me the right direction. So now this becomes one of your key responsibility as well. Uh, we are seeing that trend changing down south when I interact with students and college management in say in and around the Bangalore or say Hubli or say Hyderabad. Uh, Vijayawada, say Tamil Nadu. Uh, Now the admission thing, which used to be like 60 intake or 120 intake for EC and 1000 intake for computer science, AI/ML course, big data course, and all, collectively, now that has started dropping and people in EC has started increasing. So we are seeing that trend happening right now in India, and it will eventually be a cyclical pattern.
Yes. So hopefully we are having good time ahead for electronics,
Oh
right?
yeah, for sure, for sure.
Okay. Thanks. Thanks a
Thank
lot.
you, sir. Thank you, sir.
That's really relieving to know that we are hoping for the best time to come.
Yeah.
Sankalp, I would like to ask one question.
Sure, ma'am.
Yeah. Can you suggest any website or materials which are helpful at India level for academia that we should aware of?
Ma'am, see, this is in which context, ma'am?
In the same, because many of the students who wanted to build up their career in semiconductor domain.
Right.
So at this stage, we are not able to give them such materials. So if you suggest that any
Ma'am,
courses or any material.
I'll not say any specific course because I, as an individual, may or may not be interested in that area, right?
Oh,
I'll say, student, as a faculty or as a college staff or management, right? You should encourage students at least to be part of LinkedIn, right? They should have their
yeah.
own profile, and depending on what area of interest matters to them, they should start meeting people, following people on LinkedIn, right? Don't make it a Facebook. It is
Yeah.
purely professional. It is nothing personal there, right? So keep it professional. There are a lot of people who get benefited through that. That is a very good platform. There are, and in terms of learning, if you want to say, there are many courses available on NPTEL. There are many
Okay.
courses available on Coursera. If it is more technical or specific, if you want. But in general, if you want to encourage student, ask them to at least create their own LinkedIn profile, showcase their achievements, connect with people, try to see what is happening. There are a lot of individuals who are running community groups, right? If I have to say, in India's context, I know a guy who runs a, community called Techoveda. Uh, yeah, he keeps posting lot of articles there. There are guys who are running things on just chip design, STA, and all those things. Uh, so there are a lot of things which is available. It is just for students to or faculties to guide them and students to just take that up.
Uh, right. So actually, do you suggest any domain that we should focus for next 10 years so our upcoming students can have a job after their graduation?
Ma'am, if you ask me, from that entire chain, right, of the IC design manufacturing one slide which I have shown, if I want to
Yeah.
say, so there will be a good demand in the design space, which is already existing in India. It will continue to be there. The Qualcomms, the Nvidias, the Broadcoms will be there in India. They will be hiring people. Lot of chip designers will be required. Uh, Again, on the fab side of it, you are the best judge. If you think that you, as a faculty or as a management, have that competency available, please give a shot to that, because that will actually help students in and around Gujarat, right? Once the fabs and all these OSATs come up there. So depending on what you want to target, see, if on the design side of it, we have the biggest workforce available right now across the globe. We do the best, the latest, and the greatest chip design for all the multinationals. I can put it in that way, right?
Yeah.
Uh,
Thank you
so,
very much.
yeah, it's your call.
Yes.
So, ma'am, just a thing there. If you are really thinking for a 10-year or a 5-year plan, think for a product which you think which is already existing, not a problem, but you want to build it from scratch from India, right? If you think that
Right,
way,
right.
you will get a lot of things coming up your way.
Right, right. Thank you. Thank you very much.
Any other questions before we wrap up?
Is there anyone? I guess they asked it all, Sankalp. Thanks a
Thank
lot
you. Thank you, ma'am.
for being so informative and such a fabulous guide to us. Thanks a lot.
Thank you. Thank you, everyone. Is
Ashlesha, are you
Ashlesha?
there? Yeah. Ashlesha, are you there?
I don't see Ashlesha. No, she.
Ma'am, just a minute. I should call her.
Yeah, okay.
Hello.
Ashlesha is there, yeah.
Yeah, I'm there.
Hey,
Hello,
Ashlesha, good
Ashlesha.
evening.
Good evening.
Yeah, good evening. Good evening.
Uh, So, can you once verify, please, Ashlesha, that are you able to share your screen or not?
Let me.
Hmm.
Are you able to see? I'm able to share here.
Yes, Ashlesha, we can
Oh,
see your
yeah.
screen.
Yes, we are
Okay.
able to see the screen. So, before Ashlesha can begin, let me introduce Ashlesha quickly. Hmm. Uh, Again, she is someone who's our alumni, and I'm a proud teacher to introduce her. Uh, she completed her bachelor's in electronics and communication from V.V.P. Engineering College, affiliated to Gujarat Technological University in the year 2017. She has a total of 8 years experience in the VLSI domain. She started her VLSI journey from E-Info Chips Ahmedabad, and there she worked for 4+ years as a physical design engineer. Parallel to that, she got the chance to pursue her MTech from Beats Pilani through WILP program. Later, she joined the company called Wafer Space. That semiconductor company she joined as a senior design engineer and worked there for a year. From December 2022, she has been working with Synopsys as an application engineer. Her area of expertise is physical designing, being the part of backend designing. Specifically, she is working on PNR tools, that is iCompiler and Fusion Compiler, and supporting different customers who are working on chip designing at different tech nodes and with higher frequency requirements. As a field application engineer, she has worked with different customers to understand the requirements from the tools in terms of the different features or usage of those tools. And at the synopsis, she contributes into trying to ensure that customers can smoothly implement their designs using EDA tools besides all of the design complexities. A remarkable journey, Ashlesha, for sure, in 8+ years. Welcome you aboard.
Thank you. Thank you, ma'am, for the introduction.
So yeah, it's all up to you now. Over to you, Ashlesha.
Okay. Sure. Share my screen. Are you able to see it? Or...
Yes,
Hello?
absolutely.
Oh, okay, okay. Okay, so hi everyone, good evening to all. So today I am about to cover the overview on the VLSI design flow, and we'll cover few steps. So here I have just written out the agenda or the topics I'll be covering today. That is first is the what is the designing of VLSI chips, then why we need a designing flow for anything and specifically for the VLSI chips, then the benefits of the VLSI design flow and whatever the structured flow we have currently in the design ecosystem, what are the benefits of those flow steps, then the VLSI design flow, and then we will take a look into the details of every VLSI design flow steps. Okay, so first is what is a designing of a VLSI chips. First, we all know that VLSI chips are, its applications, it's in a very wide range. It's for all the modern electronic devices, VLSI chips have become an essential part, and it is used across all multiple domains like aerospace, IoT domains, and consumer electronics, automotive industries, telecommunications, healthcare, everywhere it is present currently. So it becomes very important that whatever the chips are getting manufactured, it allows every domain to fulfill their criteria and their specifications. So that's why the designing of VLSI chips from a starting of the flow, it became very important and very crucial, all the flow steps. So the VLSI chips are the backbone of modern electronic devices, and basically it is an integral multiple of the different electronic components. Very basic components are transistor, resistors, capacitors, and interconnects into a compact and highly efficient circuit. Because the complexity of the systems are getting increasing, the VLSI chips are also getting more complex in terms of a design. So, and the designing of a VLSI chip refers to transforming system level specifications into a complex integrated circuit using the multiple abstraction levels, design tools, and fabrication techniques. So as we go from a higher node to the lower node, this design complexity is getting increased. Though, like we have in the industry, we will have the multiple requirements, but it increases the complexity at the designing part. So that's why we'll just take an overview like what are the different parts of designing flow which are important to take a look at very initial stages. So first thing is the what are the design abstraction levels? So design abstraction levels are majorly the 5 levels are there. The first is the system level design abstraction level. Then it is a multiple level, that is a logic level we call logic level abstractions. Then the gate level, then circuit level, and then the layout. So what is abstraction? First thing is abstraction is like whenever we have multiple informations or a huge bunch of information available with us, we cannot make any decisions or any analysis on those huge bunch of informations. So for definitely for the tool, if we are using any automotive tools, for a tool, it is more complex to load all these informations at a one go and decide something or perform any optimization on those informations. So that's why this design abstraction levels are used to optimize the design at a multiple stages. So now why VLSI design matters. So VLSI design will matter because we need to improve the performance, like because transistors, as we go from a higher to lower node, transistors are becoming smaller. So as we scale from a higher to lower node, they'll operate faster, but they will add multiple complexities at the layout levels, like the DRCs or a physical verification checks. So even the design is getting faster, our complexity or to mitigate all the challenges at the end or at the layout level, it will be difficult, or we might not get the correct performances because of this, physical verifications violations there. So that's why, uh, as we go from higher to lower node, this performance enhancement has to go hand in hand from technology node improvement with the tool improvement also. The second thing is the power efficiency. So as I mentioned, like if the transistor size is getting decreased, it will not increase the speed, but also reduces the power consumptions. So that's why the efficient VLSI design will matter to improve the power optimization, and the power consumption will be getting reduced. Then the cost reduction, because now the design size is lower, so the cost per functions will decreases, and making the advanced technology more affordable and accessible. If it is if the tools and fabrication techniques all are going hand in hand, and all the steps of the VLSI design are optimizing with the technology nodes, then definitely for the innovations, or whatever the innovations are coming in modern electronics, to make those innovation into a reality, we need continuous innovation in the designing flow also. So the very basic analogy is that how the designing of any ideas will start. So every design innovation will start from a human brain, which itself is the innovation of nature and great tool to make other designs into a reality. So it is a source and the catalyst of innovation, we call. So this is a very basic analogy, like how a human mind will work. So whatever the system specifications comes into a human brain, that needs to go through all the design steps so that it becomes a reality. Okay, but now whatever the initial innovation we have in our mind are just half cooked food until they are well implemented and executed via a proper design processing cycle. And that is why this VLSI design flow becomes very essential part, and it has to be very structured and well mannered, such that whatever the design ideas or the innovations are coming in the VLSI industry, it reaches to its reality. Now, the benefits of this structured flow of VLSI designing. So, in the semiconductor industry, every single chip is expected to be fulfilling multiple specifications. Like it has to be compact, it has to be high performance device, energy efficient, or a cost effective device, and all this are expected to be aligned with each other. So to fulfill all this requirement, we need a structured flow of VLSI design, which empowers from a starting from a system level specifications to the chip designing. All the steps should get optimized further and further with the node enhancement there. So the structured flow of VLSI design will involve the systematic planning, then prototyping, and the iterative testing and refinement, so that ensuring that idea is a practical and reliable for the chip designing. It should go till the manufacturing, and the testing that should be clean with that chip designing. Now, as I mentioned, like there will be a multiple abstraction levels in a VLSI designing, because any tool or a human cannot take that much of information which currently the chip have, and they cannot optimize or they cannot analyze properly if there is a huge bunch of information available at only one place. So that's why there are multiple levels of abstractions, like the system level, RTL level, logic level, circuit level, physical layout. So as we go from higher to lower, the details of the specifications will be increasing. And here, if we take like system level or a behavioral level, the information available at this step will be very high level information, like what are the basic requirements of a frequency or the PPA power, performance and area requirement, so that whatever the tool we will be using at this particular abstraction level, it has to just focus on the functionality or it just had to focus on the particular step only and need to optimize there. I think some turned off parties. Start again. Are you able to see, or it's just moving? I think some action has been there.
You need any help, Ashlesha?
Are you able to see? Because I'm getting notifications that the presentation has been changed. The view has been changed.
Are able to see it, but I afraid it's not the entire slide that you. Yeah, this is good one. This is fine.
Oh,
You're on
okay.
the ninth slide, right? Now you were on the
Eighth
eighth.
slide.
Yeah,
Yes.
yeah, yeah. It looks proper now. Go ahead. Yeah.
Okay. Yeah, so I was mentioning that abstraction levels will define like whatever the abstraction levels we are using, that is a bunch of information that in that database it carries. So suppose system level abstraction level we are using, it will just focus on the functionality of the design specifications, and whatever the tools we will be using, it will just focus on the very higher level information, so that tools runtime or tools focus area is a very fixed. It will not go into the very detailed level of a designing or the transistor level or the layout level designing, because we do not have that information available at this level. Then we will what we will we will move from system level abstraction level to the RTL level, that is a register transfer logic levels, and that is an architecture level. So it will have multiple specifications like what all the subblocks need to go into the design, and what will be the timing constraints or the power constraints will be required. So whatever the tool will be using, like for the synthesis, that will focus on just architectural design level optimizations. So all this abstraction levels are required, and it will define the different VLSI domains also, like the front end or the back end design level. So these are the requirements. First, this is the first requirement of the VLSI structured flow for the VLSI design, such that any tool, whatever we are using, it won't get a huge amount of a data for a processing. Now, the requirement of the abstraction levels, as I mentioned, that each higher level will have the abstracts of the details of the lower level of the abstraction levels. Now, with whatever the errors will come into the higher abstraction level, it will get propagated down. That's why it's very important, or we take care that whatever level of the abstractions we have, we try to mitigate all the violations at that level only. So hence the careful verification is essential at RTL and gate level before committing to the layout levels. Now the modern EDA tools automate the translation from higher to lower levels, like the synthesis from the RTL to gate level designing, and the layout generation from the schematics. The another level of abstraction is the by partitioning the VLSI design into the levels of abstractions. Like designers can manage the complexity, then optimize for a performance, power, and area, and then systematically verify the design before it goes into the fabrication, so that our time to market will also improve, and we will not have you know uh, very long chain of the design flow execution for the chip which is not functionally correct. And this is called a hierarchical approach, and it is essential in a modern chip design where billions of transistors coexist on a single die. And the process can be automated or a semi-automated using the EDA tools to ensure the accuracy, efficiency, and scalability. So now the types of a VLSI design flow. So majorly there are two main types of VLSI design flow. One is a top to down and one is a bottom up approach. So from top to down approach, we will have first system level information, which we will go into the detail in further slides. So design process will move from the abstract level to the detailed level, so that whatever the refining we need at abstraction level or the system specification level, we will do that and we will improve our runtime there. So it will in the top-down design flow, we will focus on the system level behavior initially before refining each part of the design. And it is ideal when the system level decisions need to be made early in the design process, like the frequency of the design and the power requirement of the design. So the technology node of the designs and everything. And the second is a bottom up approach, and it will start designing from the smallest component first. So whenever we are saying bottom up approach, so definitely it will go, it will start from the below level of the abstraction levels from the transistor level, and it will then go up. So this is ideal for developing modular systems, like when where the focus is on creating reusable or a lower level components like IPs or hard macros that can be integrated later on the main design parts. So now coming to the main VLSI design flow. So here, as I mentioned, that this is a top to bottom design flow, and the system specifications we will be covering the first, then architectural design, then functional designs and logic synthesis, then we will come to circuit designing. So till circuit design, we will not have any idea about the whatever the technology node is getting used, or the uh, whatever the metal layer informations or any information related to the uh, physical layout. So once we get the circuit designs, till that at that point we will have the transistor level information here in the circuit design, and then we will go further on the physical designing flow, which have again further steps, and then there will be the physical verification and sign off, then fabrication, packaging, testing, and chip will be finally. So here I have mainly focused on the physical design flow, and I'll just give the overview on the further front-end design flow as well. So the first thing is the system specifications. So it defines the system's functionality, performance goals, and the constraints, which will be a part of our input to all other further stages as a part of SDC constraints and clock cycles, clock frequency, and whatever the IO delays will be there, input delays, output delays for the peripheral device connections, that all will go under the system specifications. And why it is required, to analyze all this system specifications here at to minimize the risk, in the further steps. And if the design is not meeting the this specifications, we will get to know in a very early stage. The next step is the architectural design. So in this step, the design will be translated from a system level specifications into a high level structural framework. So this system level specifications will be mainly in the higher level programming code, that is a C, C++, and it will get converted into the higher level structural framework or the RTL level we can tell, that will be either Verilog or VHDL languages. So in the RTL, we will have the detailed blueprint of the functionality of the design which is required to manufacture. And for translating this system level specifications into the RTL level, there are significant aspects which need to be taken care. That first is the functional partitioning. So whatever the system specifications we will be having, that system will be getting break down the system into the smaller functional blocks like the processor, memories, IO controllers, or any other unit is required. So first that will be getting partitioned in the architectural design flow step. Then the data path design and the control path design. So for all the VLSI designs, these two things are important, that whatever the data we want to pass through the design, so we need to have those flow diagrams or those connections available in the RTL level itself. And the control path design, so whatever the data path flow is there, but that will be static in a nature. So we need to make it dynamic because we want to specify that at which time my data should be available at which point, at particular points. So that's why the clock will come into the picture. Clock will be my reference point, and based on that, I need to configure my data path flow lines. So that's why the data path design and control path design is very essential, and it has to meet the whatever the chip we are fabricating. For that, will have the highest frequency range. So whatever we are designing at this architectural level, that will make sure that it is reaching to the our expected frequency. The next is the performance analysis. So in as I mentioned, like clock will be there. So for the clock also, there will be a clock latency or a throughput and the power consumptions to meet the system specifications. Means whatever the clock network I will be having in my design, it will have its own latencies and throughput or its power consumptions will be there. So I need to configure all the clock networks requirement at this level, at architectural level, and then I need to make sure that by including all these aspects, my design is meeting the highest frequency, whatever is expected there. So with all this aspects consideration, tool will do the optimizations. Means it will try to balance the trade-off between performance uh, area and the power consumption. So performance means wise the highest frequencies, and area is like whatever the floor plan areas or the chip area is given. We need to we need to meet all the requirements into that area only, because whatever the maximum number of a transistors level we can fit into it, it will it has to be such that I get the highest frequency, and I don't get the highest the power consumption should be also low, because as the number of transistor gets increased, the power consumption will also go high. But we need to align all these three aspects simultaneously. Then the next thing is the technology consideration. So we need to select the suitable technology for implementation. So factoring in a speed and power efficiency. So technology node will definitely make a very important role. So whatever the specifications we have till now, it does not have any information related to the transistor size we are going to take no further. So that's why we need whatever the foundry have defined the rules for manufacturing the transistors, that need to be considered while we are starting the optimization or analyzing the our design in terms of all this performance area or power consumptions values. So that's why we need to whatever the nodes we are using, technology nodes, we need to take those data uh, into the optimization, and then we need to see that it is meeting our requirement or not. Then the interface definitions. So it designs the interfaces for a communication between blocks with the external components. So as it is an architectural level design, the chip level designs will have to communicate with the uh, external world also. And at chip level also, there will be multiple blocks inside which will get partitioned. So the proper communication needs to be there between the sub blocks as well. So that's why the interface definitions will be required whenever we are starting the optimization at the architectural level. Then the verification plan. So the outlines of initial test to ensure the architecture meets the functional and performance goals, like whatever the timing criteria we have, it has to pass through all the verification checks through that. Now, the next step here is the functional and the logic design. So this process is a bridge between the higher level designs with the physical implementation. So till now, we have all the informations for the logic levels. We did not had any information on transistor, transistor level connections or transistor level, layout. Is transistor level layout was not present here. So here in the functional and the logic designs, after the architecture is established, the functionality and interconnections of individual modules must be specified. Then the logic synthesis tool will automate the transformation of SDL descriptions into the lower level circuit level components. As I mentioned, like whatever the abstraction, we are going from top to down. So from the system level specifications, we will come down to the logic level, then we will come down again to the circuit level, and then we will go to the transistor level and the gate level. So this tools take the HDL code and the technology library as an input, and it will generate a netlist which represents the connectivity of signal nets and the circuit elements. So including the standard cells and the transistors and whatever the IPs we are using in our design, it has to maintain all the connectivity uh, after the HDL code transformation we have. Then the next step is the circuit design. So in the circuit design, the logic synthesis and the gate level netlist generation will happen. So as we discussed, like till here we have logic level information, circuit level information is there, but still now the layout does not have the proper transistor level connectivity. So in this step, circuit design steps, we will get the gate level netlist generations, like conversion of general technology libraries to the our technology dependent library cells. So for most digital logic on a chip, logic synthesis tools are used to automatically translate this Boolean expressions into the gate level netlist, whatever the AOI or combination cells we have, that will be converted into the actual gate level design, and the output netlist will have all the technology dependent information. So, and the netlist, whatever we have after the circuit designing, it will be representing the circuit structure at the level of a standard cells or a higher, means the higher level of or IP level connectivity will be there. So ensuring the design is ready for the physical implementations. So there are two parts, like transistor level circuit design, and then whatever netlist we have generated, uh, we need to verify that what we need to verify that netlist also, because we have done multiple conversation in between. So we need to perform the verifications on whatever the netlist is generated after the circuit design or the gate level transformation. Now, so the mainly coming to the physical design flow. So, physical design flow is a process of transforming a logical circuit design, which we had till now, from the RTL to gate level netlist into the manufacturable layout design. So, in this, whatever the EDA tools we use, or Synopsys we use IC compiler tool or Fusion compiler tool, so it will optimize the design for PPA, means performance, power, area, for and the manufacturability while adhering to the design constraints. Now, this design constraints are a different physical verification checks which we need to perform during the design flow itself. So the key stages in the physical design flow are the partitioning at the system level, then chip planning or a floor planning, then placement, then clock tree or the network synthesis, clock tree network synthesis, then global routing, detail routing, then timing closures are main physical design flow, which mostly the PNR tool will perform. And after that, we will be doing the physical verifications checks to maintain all the design constraints given by the foundry. So the first step is the partitioning. So the partitioning is the process of dividing a large complex circuit into a smaller, more manageable sub-circuits of the modules. Like the system level of a partitioning, we will be dividing into the multiple levels, so that we will have an idea of that in my chip, how many memories I have, or what are the interface logics I have. So that will be taken as an input to the PNR tools. So this enables each segment to be designed, analyzed, and optimized independently, improving both efficiency and focus in the design process. So the chip partitioning during the chip partitioning, we will not have any idea that in particular memory of whatever we are using, how many transistors are going to be there, or how many standard cells are going to be there. So that's why this abstraction level information
ಓಯ್
will be very.
ಹೋಮ್ವರ್ಕ್ ಬರಿ ಅಂತ ಅಂದೆ ನಾನು.
Partitioning
ಆ
will ensure that each
ಯಾವಾಗ?
smaller section of the circuit adheres
Bhavya
to the
ma'am,
specific
please turn
design.
off your mic.
ನೀನು ಊಟ ಮಾಡುವಾಗ ಹಂಗೆ ಚೂರ್ ಚೂರ್ ಬರಿತೀನಿ.
So, partitioning will ensure that each smaller section of the circuit adheres to the specific design constraints, and it helps to reduce the overall design complexity by isolating the problems and streamlining the design flow. Because whenever we are doing the chip level partitioning, we need to ensure that whatever the floor planning or placement of the memories or placement of the processor we are doing, it has to there should be less interconnects or the less congestion into the chip level interconnects flow. So the chip planning or floor planning. So chip planning or floor planning is the here whatever we will have the area definitions from very starting, so we might not be able to increase or decrease the chip area. So whatever the area we have, based on that we need to make sure that whatever the systems we want to integrate here, it is integrating into my design by and meeting all my PPA criteria as well. So it is a strategic arrangement of the various subcircuits, modules, and IPs blocks within the physical layout of the chip. So as we think, like if we want to uh, construct one building or something, what will be the basic requirements? That will be we should have land first, and then we can define any floor plan or any architecture for that building. So similar way here for doing a chip design planning, first we should have a specific chip area defined on, so that we can decide what memories or what sub-circuits will be placed at which locations. So, effective floor planning will optimize the chip's area efficiency, and it will minimize the interconnector delays, and it will overall enhance the performance by ensuring that the modules are placed in a way that facilitates efficient routing and power distributions. So this is just a very brief idea about the chip planning here. So in the chip planning, like floor planning, there will be number of standard cells which will be required for our design specifications. But apart from that, also we will have to add multiple physical cells which will be required for a manufacturability for the manufacturability of the design, like multiple physical cells, because once the chip goes into the fabrications, there will be multiple limitations of the foundry also. Uh, and as we go from higher to lower node, this limitations will increase, and that's why we need to make sure that whatever chip area we are giving, it is meeting the foundry requirements also. And inside the chip also, we should be having multiple cells which foundry have recommended, and we should follow all their rules. So that's why this corner cells or IO cells, bond pad cells, and the physical, there are other types of physical cells also which we need at every chip level floor planning or sub block level floor planning, so that at any point a design doesn't go into the any functionality failure stage, or it does not get heat, or it does not get shows open physical verifications violations. So basically, in the floor planning step, we will define the block shape or a size, then whatever the voltage area requirement is there. Now, for a single voltage domain, the complete chip will be, or complete block will be working on the single voltage. So for the single voltage, it is not that much complex, but when we go into the multi-voltage domain designs. So for that, we will have to define the voltage area, like the physical area of the voltage, such that like whatever the cells or whatever the IPs which are using the lower, suppose there are higher higher level of power and lower level of power is available. We need to make sure that both the power domains are available in the design, and they are meeting all the requirements from the foundry also. So that's why these voltage area shapes and locations are important to give at the floor planning stage, so such that the standard cell placement and further hard micro level placement will be considering this area specifications here. Then in the floor planning steps, we also give the macro cell locations, hard macros to be fixed, and IO pin locations, whatever the peripheral communications is required for the chip level or the block level, that will be done here. Then placement blockages. So these are the terminologies will be required for, particularly for a tool, different EDA tool, to understand that how to optimize the design to meet my requirement for meet my power or area requirement. Now, what will be the inputs going into the floor planning stage? So, as we had discussed, like till the floor planning steps, we had just a logical information available with us. So that logical level informations will be available as a netlist files, and it will have all the logical connectivity of cells or blocks. Then in parallel, we will be having the dot left files, which is geometric informations of the standard cells, macros, and the different IO pad cells or the different physical cells. So this file will be coming from the foundry, and it will be dependent on the technology node what we are using. So then this is required because now we are converting our logical level information into the physical level informations. So whatever the gate, suppose end gate we had in our net list, now we want to map it with the geometry of the end gate. So suppose like whatever the drawing we had in our paper, now we want it actually in the actual design. So that's why this left file is a required. So left is a just a layout exchange format. So previously we had the logical layout. Now we wanted to convert into the physical layout. So for converting that end gate from logical to the physical, we need this left file or geometric information of particularly that end gate, like how many pins are there or what will be the direction of the pin, what will be the size of that gate. So every information will be available in the physical libraries of the left file. Now the something is the timing libraries for delay and functional characteristics of what and we will be having multiple timing libraries based on the corners we give. So this will have the information of whatever the end gate suppose we had. Now the end gate will have its input to output path and how much delay one single cell will will be coming in the layout. So that information will be available in the timing library files. Then the technology file, so it will include the metal layers and the design rules. So this is required for the manufacturability of the design. So to meet all the design rule constraints like the minimum spacing or minimum width rule or the routing rules, different routing rules, it will be a must input for our before starting the floor planning itself. So it will have the different metal layer information as well. So as we have discussed, like the chip area is fixed, but whatever the connections we are going to make between two different cells, that will go horizontal and vertical from on the higher level, like the metal different metal layers. From so based on the technology node, the number of metal layers will be different. So that's why the technology files will be, dependent on the node, and the metal layer width and metal layer length will be different as per the node changes. Then the next is the design constraints, so like the clock frequency requirements, then the setup hold requirements, and the path constraints. Like so, one thing we have discussed in the architecture level is like there will be two things. One is the data flow fly lines, and the second is the control path. So data path, as I mentioned, it will be static, but using the control path, we are making it dynamic. And so now the path constraints are also required because in the design, all the paths, all the connections must not be turned on at every time. So that's why we specify some path as a false paths and multi-cycle paths, so that all the design related constraints will be covered into the .sdc file. Then the power specifications. So this, if we have the multi-voltage designs, so we need to create multiple power domains in the design during the floor planning step itself. So that's why we need a UPF file. So it will define that what particular sub blocks or what particular part of the chip is it has a what how many power domain requirement or what power domain requirement is there. So that will be required. Then predefined floor plan constraints like core and die size, then aspect ratio, then utilization targets to meet the chip area requirement. So these things are like, whatever the inputs or whatever the requirements of the chip we have. And these are our basic inputs for, to start for the PNR stage. So after the floor plan is done, we will have the design which has all the sub blocks are placed in the designs, and for this particular single block also, it has if it has a hard macros or any IPs in the design, it will it will have all the locations available for the all the physical layout informations. Then the next step is the placement. So whatever the layout we have in the floor plan step, it will have all the placement information available for, but for the standard cell, for the transistor level placement, it's still not done, because we'll have billions of transistors and we have just done the placement of a sub blocks or any IPs or any hard macros. So in the placement stage, now all these standard cells will get placed into the design, and if the hard macros are not placed until now, it will also get placed into in the placement stage, such that it minimizes the interconnect path and it meet the our PPA targets as well. Then the proper placement will minimize the delay, improve the power efficiency, and contributes to a more compact and functional chip design by ensuring that cells are properly placed there. So this is a basic checks for the placement, like before we start for the placement steps, there are several requirements, like whatever the design setup means like whatever the constraints we are giving here, all these constraints needs to be accurate or needs to be correct. Otherwise, whatever the optimization will happen, like suppose we have given some wrong, data into the design, so tool will unnecessary do optimizations, and it might not reach to our PPA target. So that's why a design setup is a very important part. Then we perform some pre-placement checks. So the pre-placement checks are the basic checks, like whatever the hard macros are there, those are already placed in the designs. Or there are several aspects of floor planning as well, like the floor plan site row creations and track creations. So all these checks needs to be uh, clear before we go for the placement stage. Then the design and flow requirement setup. So for doing this PNR, we are definitely going to use any tool, EDA tool. So EDA, now how the EDA tool will work is like we have given all these files and informations, but tool have its own way to understand this all information. It will take all these files as an input, but apart from that,
10% ડિસ્કાઉન્ટ કરેલું જ છે ભાઈ. હું દર વખતે બુક લઈ જાઉં છું. કઈ ગયા પેલા ભાઈ?
પ્લીઝ આના પર વાતચીત ન કરો. ધ્યાન રાખો તમારું માઇક મ્યુટ હોય એવું. યુ આર ડિસ્ટર્બિંગ અધર્સ, પ્લીઝ.
designer, so I was mentioning that whatever the inputs we have already as a, in terms of files from either from the library vendor or the standard library vendor or from the foundry, that is there. But to make the tool to understand my requirements, there will be a several different ways also, like there will be some, flow setup will be required, like the attributes or options I need to give to the tool, so that tool can understand that what design specifications I need to try to optimize further. Suppose if I give you an example, if one chip is there, it is the customer wants to optimize in terms of a timing more, they are okay with the whatever the power it consumes, so that input I will not have from this files. Power requirement is there, but focus area where I need to give that informations I will not be having as a part of any input files. So that I need to give to any tool as part of the flow setup or the tool setup. So there will be different app options or different commands to take care of those settings, that uh, I will command the tool to just focus on the timing, irrespective of whatever the power consumption happens in my design. so that tool will understand and tool will try to optimize the design for timing improvement. So this will be a iterative process, and whatever after like once we do the placement, we'll have the QR available. Quality of results will be available with us for all the specifications like power output and then timing violations, DRC violations, and everything. So based on this QR analysis, this process will be iterative. What if it is not meeting to my requirement, I will go back and I might change the setup. I might do perform this checks and see if there are any violations are there, and then I will run the placement until I don't get the satisfied result at the placement itself. So that's why tool are also emerging, like because this is a very initial step of a designing or for the physical designing mainly. So to ensure that whatever the challenges are going to come in the further stage, I'm trying to fix it in a very early stage, and that's why the proper usage of all the EDA tools is important. And that's why the previously whatever the IC compiler tool we had, it was just doing the placement law physical synthesis, logical synthesis, but now we have the fusion compiler tool which does the logical and physical synthesis both. Means the during this logical optimizations, I can give tool, I can give command tool to make understand that whatever the hard macro locations I have. Suppose if I say when I was optimizing at this level or functional or logic level designing, till in the conventional flow, I did not had information that what will be my hard macro placement or hard macro location is there in my chip. But now using the physical synthesis, we have facility to tell the tool that I'll be using this particular macro placements or standard cell placements. So based on that, tool will try to optimize further, so that this iterative process will become a minimal, and turn around time will improve to reach our criteria there. So once we have the placement completed, we will have the design, which is completely placed. All the standard cells, all the micros, everything is placed into the design, and it is well optimized or based on our inputs we have given. So now our all the data path logic is available, and then we need to go further for the CTS stage for control path logic building and its optimization. So now with the placement of the standard cells, there is another phenomenon which is a DFT, that is a design for testability, and whatever the data path logic we have, apart from that, we need logic from it, for testing purpose also, and which is required at next for, or the last level of the manufacturing, or once the chip is manufactured, we need to test the chip, and for that we need to enter particular logic into the design. So that need to happen during the placement stage itself, because whatever the cells we are going to add in the design, that need to be placed properly at the placement stage itself, to ensure that during the testing we do not get any issues. So that's why the importance of DFT is there in the physical design of flow itself, and it has to be covered during the placement stage itself. So this DFT technique, there are several DFT techniques as well, and it will facilitate the generation of a test patterns that can effectively verify the functionality of the circuit at the later stage once the chip is manufactured. So this is particularly important for a complex designs where traditional testing methods may be insufficient, because the complexity is getting more increased, like for the low power designs also, and for the lower node designs also. Next is the controllability and the observability. So DFT logic will ensure that internal states of the circuit can be easily controlled and observed at any level of the abstractions. So this is achieved through techniques like scan path designs, where flip-flops are placed with a scan flip-flops. So the normal flip-flops will not have all the pins, but the scan flip-flop will have some testing pins which will enable the chip to go into the particular scan mode so that the chip can be tested out in the later stages. Then the integration with the physical design. So DFT is integrated into the physical design flow, where it is essential to maintain logical equivalence between RTL and gate level netlist also, because in the RTL level we discussed like all the logic level information is available at the RTL level. Then we have converted that hard HDL language for that to gate level netlist, so that we have all the technology dependent logic with us. Now again we are inserting some logic. So we need to make sure that whatever the logic we are entering into the adding into the design, that is meeting all the technology dependent criteria. And after inserting also, we need to make sure that those are properly placed into the design. So this integration helps in the optimizing the design for a power, performance, and area, while ensuring that the DFT logic does not adversely affect the overall design. Because if the chip design is very complex, and the DFT logic itself is a very huge amount, huge. So the area which is required for DFT logic will increase, which is not going to help in our functionality of the chip. It is just required for the testing purpose. So we need to ensure that whatever DFT logic we are adding into the design, that is optimum for the design convergence. Okay, so we have the our design is completely placed and optimized now for the data paths, and now we need to ensure that whatever the control paths we are trying to meet, for that we should have some reference clocks available. And for a clock, now the clock will this reference will come from the external world, so that will be that will be connected from the as an interface port or something like that. So we need to make sure that whatever the clock is there, it has to reach to the all other standard cells till the standard cell level design. So suppose if I give an example, so suppose my clock port is available in one of this region, I need to make sure that this clock should reach all all the locations of the chip without affecting without affecting the data flow tilings there, and without you know affecting to the my clock frequency. So the process of designing this clock distribution network within a chip is called the clock network synthesis, and it includes the buffering, gating, and routing of the clock signals, and carefully managing the clock skew and signal delay to meet the stringent timing requirements. So conventional flow was the clock mesh flow, where from in that from single port we used to create a mesh of the clock, and then we need to we were to distribute the this clock path to all near to all the standard cell spins. But we have different clock tree styles also available. So we need to ensure that whatever the clock tree styles we are using in our design, it is meeting our timing requirements and the power consumption requirements as well. So there is a H tree model also. There is a MSCTS fan out balance tree model available. There is a spine and trunk model available. So this all models trying out, we need to try out, and we need to finalize that module that which is giving the best results. And the clock tree network synthesis is very important part in physical design also, because the clock is very dynamic in nature, and it has to be turned on at every time. So the power consumptions which clock tree will take, it will be the highest. So that's why we need to make sure that whatever the clock tree styles we are using, it is meeting our power requirement also, and it is meeting our area requirement also, because clock has to reach on time at all the standard cell levels. So that's where the setup and hold the time also comes into the picture. So that's why this is a very important part into the power analysis for the physical design. Now, after the clock tree building, first we will route the clock tree also into the design, because we want all the standard cells. So all the standard cells will have the clock pins, and uh, it will be so the standard cells will be at a very lower level. Like if we tell the number of metal layers, suppose there are 14 metal layers in my chip, so clock port might be at the top level, top layer. Suppose M40, M14, M13 layer have the clock port definitions. So from M30 to M0, or M1, wherever my standard cells are located, standard cell pins is available, I need to make sure that this clock routing is going from a top to down layers, all the layers. So for the routing of any signals or any clock, we will be having this routing grid into the design that tool will generate. So so that tool will understand that from which locations either it can route horizontally or vertically in the design. So for the general routing phenomenon, which tool EDA tool will be using, that is a global route and detailed route. So first, the global routing will involve the allocation of all the routing resources for interconnecting different modules and components on the chip. So whatever the hard micros or whatever the standard cells we have available in the design, first tool will try to just doing a global route, it will just try to make a connections anyhow. Uh, it will not try to meet the routing guidelines from the foundry or from the tool. Then the assignment of routing tracks. So the routing tracks we call as like whatever this checkbox you are seeing, that is called the one routing grid, and the routing tracks will be vertical or horizontal, as you can see here. Like suppose whatever this red mark is there, that is a vertical routing layer, and yellow is there, that is a horizontal routing layer. So tool will try to map. So in during the global routing, it will try to make this connections by including all the vertical global routing tracks just virtually. It can have multiple overlaps also, and the design rule violations also, which it will fixed next in the detailed routing. So in this global routing, it will just do the assignment of a routing tracks in a channels, and it will assign the specific metal layers and the tracks for each signals. So as we are telling, like whatever the standard cells we will have in the design, so it will be at a very base layer. So and if we have the 14 metal layers in the design, so standard cells will be placed at the very lower layer or base layer, we can tell, into the design. So standard cell pins will be either in M1 or M4 layer. So all these connections cannot be in just a single layer, because we will not have that much area available. Area is a fixed in the design. That's why if the tool have flexibility that two cells are placed nearby which are logically connected, still the due to the limited routing resources, tool will have to route through higher level, and it will have to come back to the lower layers. And that's where the routing congestion phenomena comes into the picture. And that's why the tool will have to do multiple iterations to fix the congestion issues or the interconnect shorts or open issues. So this iterations will be done during this detailed routing. So detailed routing is the phase where the global routing plan is refined by assigning the specific metal layers and routing tracks to each connections. Then the step ensures that the designs is a manufacturable, as I mentioned, like whatever the inputs we are giving here as the in the tech file, we will have specific design rules, like the whatever the metal layer routing we are having for the signals, it should have some minimum spacing between those two nets. So those kind of routing rules will be getting fixed during the detailed routing steps. All routing constraints are met, and including the signal integrity issues, like we cannot have a very long route in the design in a single layer, because it will uh, harm another nets nearby also, due to the coupling capacitor effects and everything, because all this routing metal layer will have metal is just about the resistance and capacitance. So later on we will take a look into that. So there are physical verification checks related to the signal integrity also, and whatever metal layers we have after this routing step. Uh, Based on that, tool will calculate the RC values and the coupling capacitance values between the two different nets. So, but we cannot just route the just do the detailed routes in this step, and further we get to know that okay, this routing is not proper, and it is violating the signal integrity checks, or the spacing violations are there. So that here the tools are enough mature that it will understand all the requirements from whatever the later stage into whatever will be there in the later stages of the flow, so that it will try to optimize it here as well, like the signal integrity, resistance, capacitance, and physical limitations of the manufacturing process for the spacing and the minimum width requirement. So the detailed routing optimizes the final layout by minimizing the routing congestions, then reducing the power consumptions, and ensuring that the chip functionally reliable. So it can create multiple issues, like the two nets can get short with each other. So based on that, my calculation will go wrong, or functionally it might be incorrect when I have any opens in the design. So the detailed routing steps will ensure all the specifications and all the criteria which we have given as a part of this all these files. My design setup, this I can call as a design setup, and for the flow setup, whatever we have given, like the commands or any options for the tool to optimize further. So tool will in the detailed route, tool will try to optimize the design in an effective way, such that we get our desired output or the GDS layout. So after detailed routing, we have the our complete logic level is converted into the physical layout, GDS, and we have all the information of transistor level, and all the interconnect level information is also available with us. So once the chip is ready with the routing, we need to perform different physical verification checks, like the because we have this physical layout with us. So the to ensure that the electrical and the logical connectivity of the GDS layout, which is generated after routing. So the first requirement is the design rule checking. So this DRC rule checking will ensure that the design can be fabricated without any defects further, and that would compromise the performance or the manufacturability. So like the spacing and width I had mentioned. Then this involves verifying the minimum spacing between the components, layer thickness, and other physical design rules, which is present in the text file, which is given from the foundry. Now, additionally, DRS checks the layer density to ensure compatibility with the chemical mechanical polishing. So this process is generally a fabrication is the fabricating chip processing, but as we need to make sure that chip has to our layout has to be ready for manufacturability. So all this checks has to be part of our tech file, so that while designing this layout only, we take care of all these rules. But still, after routing, we will be, there will be such rules which our tool is not able to fix automatically. So we need to, either make a manual efforts, or we need to, give a semi-automated methods like scripting or something to fix those particular design rules. Then the layout versus schematic checking. So that is called LVS checking. So this checking is a verification process for that compares the physical layout of the design with the original schematic to ensure the functionality is the consistent between the both the layouts. So from the layout, a netlist is generated and compared with the netlist created during a logical synthesis or a circuit design, which was the front-end level abstractions we had. So generally it checks for the shorts or opens in the design, and we need to make sure that it is getting fixed before we go to the takeout phase. Now the third thing is the parasitic extraction. So one thing is we have in the after the detailed routing, we have all the routing where the physical information available for all the connections. But to check the timing, like because at the logic level, whatever the timings we are checking, like after the RTL, whatever the timings we are seeing, whatever the frequency we are getting, that we might not get here, even if the specification and all things are same, because now the actual metal interconnects are present in the design, so that it will have its own delay value, which we need to calculate on this detailed routed design. So that's why we need this parasitic extraction process. So this process is useful to determine the electrical parameters of the layout elements, as like whatever the metal routings we have. We need to calculate the resistance and capacitance values, and we need to understand, how much amount of the capacitance or resistance is available in the designs, and what current will be flowing through those connections. And based on this informations, we need to calculate the delay values of that particular interconnect. Okay, so the one thing is like how we will define, that my design will work on my design. So maximum frequency, highest frequency, what design can achieve is based on this only, like whatever the combinational logic we have in the design. Uh, what is the maximum delay I have in the design? Based on that, I can say that the maximum frequency I can achieve by this value. So once we have these extracted design of the routed netlist, the parasitic elements are incorporated into the netlist and used for a further analysis to verify the electrical characteristics and overall performance of the circuit. So for this extractions, we will be having a different tool. So for till this point, for to do the PNR, we will be using the PNR tools like for Synopsys, as I mentioned, Fusion compiler tool is getting used, or IC compiler 2 tool. For this different physical verifications checks, we can use the ICV tool, IC validator tool as well. And same for this extraction of this layout, we will be having a different tool that is we call as a star RC. So after we get all this information, there will be some outputs will be generated, which will have this information of resistance, capacitance, and the coupling capacitance values. Based on that, we need to give this data to the another sign-off tool, which will be the timing analysis tool. So that can be a prime time tool, and based on this actual routing information we have, based on that, prime time tool will calculate what is the actual delay we will be having on the based on the layout we have available with all the routing information. So then there is another physical design rule check, that is antenna rule checking. So antenna rule checking will address a potential issue known as the antenna effect, which occurs during the plasma etch process during the chip fabrications. So whenever we are uh, fabricating at the fabrication steps, when we are fabricating from the uh, top metal layer to the down metal layer, so first, there will be a different level of mask available for metal layer fabrications. So when we fabricate from top to down, there will be some charge will get accumulated for the lower layer fabrications. And if we have the routings available, suppose this routing tracks we have for different metal layers, and if we have some routing track which is routing from suppose M14 or M13 directly to the M2 or M1, which is a very lower layer. So whenever this kind of routing we have in the design during the fabrication, the charge will get accumulated because so when we have the higher layer, that width will be higher. So the charge accumulations will be higher for that higher layer, fabrications. But for the lower layer, the thickness will be very less. So that charge will get accumulated into the lower layer, and that's why. But the lower layer does not have the proper conductor carrying capacity, and that's why it can create the issues of the shorts or opens in the design. So that's why to encounter this fabrication issues during the layout creations, we need to source these antenna rule files, which it is generally a ratio of metal area to the gate area, because all the standard cells will have its gate length available, and we need to make meet this antenna ratio. So this effects can accumulate excess charge on the metal wires that are not connected to the PN junctions diode nodes, and potentially causing the damage to the transistor gates. So if our gate will damage, then the transistor will not work properly. So that's why this is very important check. And antenna rule checks ensure that the metal traces are appropriately connected, preventing charge buildup at any stage, because whenever the metal layers are going to fabricate, it will have specific metal thickness with it. So any charge buildup or any charge flow during between the different metal layers, we need to prevent that, and we need to make sure that any gates or transistor level circuits should not get damaged while fabricating it. So as we go from higher to lower node, this will increase the complexity of the design rule violations, and to fix this antenna effects there. The next is the ERC rule checking, that is electrical rule checking. So it verifies that circuits power and ground connections are correctly established. So this power ground connection creation is also a complete different, we can say, key steps in the physical designs, which I've not covered here in detail, but generally we do the PG planning, that is a power planning, during the floor planning step itself. So before the clock trace and after the floor planning, we do the power planning, because definitely the clock needs to reach to every standard cell. Power and ground also needs to reach every standard cells in the design. So this rule will ensure that our PG connections are correctly established, and ERC ensures that the electrical integrity of the design by identifying issues like excessive current and incorrect signal timings, or power delivery between the different power domains are correct or not. So the same way, like we cannot directly suppose there are different power domains in my design, and there are standard cells. So it, the standard cell size is very less, and the gate size will be even less. So I cannot directly connect that smaller the power pin to my the higher layer power connections. I need to make sure that whatever the power from higher layer is coming, it has to properly propagate through the lower layer. Then once I have all the physical verification checks cleared the design, the part is coming the time closure. So the timing closure will ensure that the circuit operates at the desired speed without violating any setup or hold time constraints. So this setup and hold time constraints again refers to the my data path enablement and the control path. So uh, this closure is required to ensure that whatever speed is expected from a design, it is meeting or not, and making it a critical phase for achieving the optimal performance and reliability in the final design. Now, timing closure is the process of fine-tuning the design through specialized placement and routing techniques to ensure that all timing requirements are met. So all this, like whatever the PPA targets we have, performance, power, and area, we need to make sure that whenever we are starting for the physical design flow, what is our focus? It is either a timing, power, or performance in which condition we want our tool to work. So that's why if we are able to properly align this requirement, so we'll get the our required output after the detailed route or on the GDS layout design. So this includes optimizing the delay paths, adjusting the placement of a cells to minimize the critical path delays, and refining the routing to achieve the necessary performance levels. So after completing all this PNR steps and the PV checks, design GDS layout is ready, and further it goes for a fabrication testing and then post layout verifications and the packaging steps further. Now the challenges in the VLSI design flow. So although this VLSI design flow is very well structured currently, but still as the technology node is shrinking down, we will have different challenges coming up. And so what are these challenges we are having right now in the VLSI design flow? So that first is the increasing complexity. So VLSI designs are becoming more complex as the chips integrate millions of transistors, and managing this complexity requires advanced tool and techniques. So whatever the tool features we had for the higher node, that might not help to meet all the requirement which we have currently. So that's why the technology node is getting shrink down, and to align those nodes, we need to make a tool also more advanced. Then the time to market pressure. So the rapid pace of technological advancement forces companies to shorten the time to market, and the designers need to optimize each stage of the design flow without compromising on a quality. So when we say this time to market, like the whatever because we in the VLS in the design or in the specifications, we have millions of transistors, and we have millions of data with us to process for the tool. So the runtime, or like we running complete all the steps, like all the PNR steps, if we are running, it will take several days to complete and to get these DDS layout out with us. And if tool is not enough advanced, or if it's not enough matured, this runtime or runtime of getting the layout out will take more. So that's why it is important to in this flow that we ensure that whatever the setups or whatever the tool we are using, we are making best usage out of it. Then the thing is the power management. So power consumption is a critical issue, and especially for mobile and portable devices. So the design flow must account for power optimizations to meet performance needs while reducing the energy use also, because every transistor is is going to require the power, and that's why if we are increasing the number of transistors in the design, we need to make sure that how to optimize further and further, uh, and without affecting to our basic requirements of our speed or energy. Then adapting to the technology scaling. So as a semiconductor technology advances, new design challenge arises, such as adapting to smaller manufacturing processes and new material technologies. So this, like once we specifically, if I give an example, if we are moving from 130 to 4 nanometer till that time, we had some proper flow for floor planning, but when we are moving from 4 to 3 nanometer, there are multiple changes which is happening in the floor planning step itself, which is which is related to the manufacturing process. Because after the 4 nanometer, if we are coming to 3 nanometer, the manufacturing process are not that much mature that it can create that small transistors, or there are some advanced rules are coming which we need to follow to if we want to design the chip in the 3 nanometer. So to to get all to understand all the advanced rules and make the tool to work on with those advanced rules, it is a tedious process, and that's why this even though we have this PNR tools with us, the all the inputs data we have, but still it takes takes time, and it's iterative process to get the desired output at on the layout whatever we have on paper as a logic or as a system specifications. So the future trends in the VLSI design too. So now the VLSI design too is shaped by all the advanced nodes, and it is continuously evolving. So first thing is the system level design itself is getting more complex. So we need to make sure that system level design optimization is itself like at a very higher level, such that the lower level abstractions will not get more complex. So the as design grew more complex, the system level design methodologies are becoming more critical, and this approaches helps designers to explore the architectural options which were discussed in very starting, and optimize the system as a whole before diving into the detailed designing. Because once we have dived into the detailed designing, we have a bunch of data available with us for the tool. It is very hard to meet all the optimizations with this bunch of data, with this much detailed level of the abstractions. So it is very important that the system level design its advancement happens what with the complex VLSI chip designs. The second thing is design automations. So as VLSI designs is becoming more intricate, automation tools will play an increasingly important role, and these tools help streamline the process and reduce the human error or boosting productivity and design accuracy. But yes, as I mentioned, like it all has to go in line with our specifications and everything. That will be automated, but that is still a semi-automated, we can tell. So human intervention is required, and it requires the proper inputs to be given to the tool, such that we get the desired output from the tool. And the heterogeneous integration. So combining different technologies and materials on a single chip is a growing trend. So as we I think yesterday in yesterday's lecture it was mentioned about 3D ICs and everything. So that's why the design flow also has to make sure that in the single chip, if there are multiple tech nodes are getting used, it this flow should be smooth lined for the proper implementation till the layout. Uh, okay. the design flows needs to accommodate the unique challenges this integration presents, such as managing heat and interconnects. So then these emerging technologies like new fields such as quantum computing and other AI computing is available. So it will have a very big data for the tool to consider and to optimize. So that is why the conventional flow might not work better, and the continuous innovations are required to in the VLSI design flow itself and for the advancement of the design automation tools also. So yeah, this all the information I had related to the design flow. So if you have any questions, yeah, we can take it. Yeah, Ramesh, any?
Is there anyone who's having a query?
Mm.
Ashlesha, such a long but very, very effectively given session. Hats off to you for the session and a heartfelt thank you.
Thank you, thank you. It's my privilege to give it.
And we are again, as always, so proud of our alumni.
Mm. Thank you, thank you.
Okay, just in case if anyone isn't not having the query, we would end the session. But before we end the session, let us all turn on our cameras.
Okay.
I request all of you to turn on the cameras, please.
அடுத்த நிமிஷமே அம்மா கிட்ட போட்டு கொடுத்துருவாங்க.
The link of the feedback for the session 1 has been already kept in the WhatsApp group. That's been sent to the email as well. And now for this session, the feedback link will be shared soon. One more time, thanking Ashlesha for this wonderful session. And we are ending the session now. Tomorrow on our day 3, see you all soon at 6 p.m. sharp.
Thank you, ma'am. Thank you, everyone.
Thank you, Ashley sir.
Have
Thank you very much.
good night.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am, very much.
Thank you, ma'am.
Yeah, closing the
Thank
session.
you, ma'am.
Have a good night.